Dear student, today we will learn reversible reactions. What are the reversible reactions? Dynamic equilibrium is also a topic, but now at this stage we are not discussing the dynamic equilibrium. We are only discussing the reversible reaction and irreversible reaction. What are these? The definitions of these two will also be discussed here, and examples will also be discussed and mentioned. This is the definition. Most of the reactions in which products do not recombine to form reactants are called irreversible reactions. They are supposed to complete and are represented by putting a single arrow, which is indicated here. A single arrow between the reactants and products. These will be the irreversible reactions, and the example of irreversible reactions is mentioned here. This is the example of a irreversible reaction, a reaction which cannot proceed in reverse direction, which can only go in forward direction. 2H2 plus O2 goes to form 2H2O. In ordinary conditions, water has not the tendency to decompose in its constituents that are hydrogen and oxygen. It can be done, it can be reversed, but in a special condition which is called hydrolysis. And in hydrolysis we have to pass electricity through water to decompose it in its constituents, which is electrolytic process. But in normal conditions it will not be reversed. Hence, at the same time, the reactions which can proceed in both ways at the same time in the same conditions are known as reversible reactions. Hence, this reaction, when water is formed by hydrogen, by the combination of oxygen and hydrogen, it can be reversed, but not at the same time and simultaneously moving in forward and reverse direction. But it can happen in reverse direction only in the electrolytic cell, which is known as hydrolysis of water. And now we are going to discuss the next definition, the definition of reversible reactions, which is our main topic in this chapter. The reactions in which products can recombine to form reactants are called reversible reactions. These reactions never go to completion. They are represented by a double arrow, which is indicated here with a double arrow, one arrow up and one arrow down, one pointing towards from left to right and one pointing from right to left, between the reactants and products. This is the definition which is highlighted here. These reactions proceed in both ways. They consist of two reactions, forward reaction and reverse reaction. The definition is indicating that the products can recombine to form reactants, but this will happen at the same time under the same conditions simultaneously, and the rate of forward and reverse reaction becomes equal. Now we are discussing the example here. Our example number one starts. Example number one starts from here. Let's discuss a reaction between hydrogen and iodine, because one of the reactants, iodine, is purple color. Which one is of purple color, you know? Because iodine has purple color. Here is the iodine, and we have mentioned it with its color. Iodine has purple color, and purple color is encircled around iodine. Here the iodine, which is in the equation, you can see that the iodine is purple color in this reaction. And if you see that the reactants are hydrogen and iodine, both of these are gases, and the product is hydrogen iodide, which is also a gas. Two gases combine to form one gas. Hydrogen and iodine combine to form hydrogen iodide. This reaction can be considered as a reversible reaction. Example of reversible reaction: because hydrogen and iodine combine to form hydrogen iodide, at the same time hydrogen iodide decomposes to form the reactants that are hydrogen and iodine, and it can be started from reactants, also from the products, and we will reach the equilibrium position. Here, let's discuss the reaction between hydrogen and iodine. Because of one of the reactants, iodine is a purple color, while products hydrogen iodide is colorless. Both of these, oxygen and hydrogen iodide, both are colorless. Here, hydrogen is colorless also. Hydrogen iodide is also colorless. Both of these gases are colorless, and if you notice that the purple color is coming, it means purple color is becoming more and more concentrated. It means that the iodine is producing, and if the color of purple color fades out, then it means that iodine is consuming. Hydrogen iodide is formed. Hydrogen iodide is formed as a result. Purple color of iodine fades as it reacts to form hydrogen, as it reacts to form colorless hydrogen iodide, as shown in figure 9.1. Figure 9.1 is ahead. We will see that here you can see hydrogen and iodine are combining to form. This delta sign is indicating that heat. We have to provide it some heat. Here the delta sign, the sign of delta is indicating that this is the condition. This is the condition, and condition is heat. Delta is the symbol of heat, that we have to provide heat to this reaction to proceed in the forward and reverse reaction. Vapors in a closed flask, hydrogen iodide is formed as a result of purple color of iodine fades out in the reaction to form colorless hydrogen iodide. As shown in the figure, hydrogen and iodine goes to form hydrogen iodide. When iodine consumes, its color in the mixture fades out. This reaction is called a forward reaction. On the other hand, when only hydrogen iodide is heated in a closed flask, purple color appears because of the formation of hydrogen vapors. Because of the formation of iodine vapors, such as here you can see that hydrogen iodide, a colorless gas, is in hand, and the delta sign is indicating that we have to provide heat to the reaction. We have to provide heat, and the next is hydrogen, which is also colorless, and purple colored iodine. Iodine has purple color. If this reaction proceeds in the forward direction, from left to right, you will notice that the purple color appears. Purple color appears in the mixture, and you notices that hydrogen and iodine are forming by the decomposition of hydrogen iodide. It means that the reaction can proceed in both ways. In this case, hydrogen iodide acts as a reactant. Here, hydrogen iodide is a reactant and produces hydrogen and iodine vapors. This reaction is reverse of the above. Therefore, it is called a reverse reaction. When both of these reactions are written together as a reversible reaction, they are represented as hydrogen plus iodine reversibly goes to form hydrogen iodide. H2 plus I2 reversibly goes to HI, means hydrogen gas and iodine gas combines to form hydrogen iodide gas, and hydrogen iodide gas at the same time decomposes to form hydrogen and iodine gases. Here we go. Now this is the equation. Here you can see the purple color of iodine. This is iodine, and here is the colorless hydrogen. Both of these combines and form hydrogen iodide, which is also colorless. Here is the example number 2. We are going to discuss the example number 2, which is the example of a reversible reaction. This is also a reversible reaction, and here some new details will be discussed. In this reaction, one thing which is carbon dioxide is gas, and other two are solids. When calcium oxide solid combined with the carbon dioxide gas, it will form CaCO3, that is also calcium carbonate, that is also a solid. And in this example, you will notice that when carbon dioxide is available for this reaction will happen, and if we will allow carbon dioxide to escape from here, it will be completed. It will complete, and the reaction will not attain equilibrium state, and hence it will be irreversible reaction. It will behave like irreversible reaction. When CaCO3 calcium carbonate is heated in an open flask, the decomposition it decomposes our decomposition happens to form calcium oxide and carbon dioxide, the reverse of the above, and carbon dioxide escapes out and the reaction goes to completion. Here you can see that the reaction is decomposition reaction because CaCO3 is solid and CaO, which is forming, is also solid, but carbon dioxide is not solid, rather it is a gas and it can escape easily. Here you can see that the CaCO3, when it is heated, carbon dioxide is being formed and carbon dioxide will escape out because it is a gas and it will escape out from here, and the residues will be only CaO, which cannot be reversed to form CaCO3. It can only be reversed if CaO and CO2 both are available for the reverse reaction, and hence if you try to attain this reversible reaction in an open flask, then you are trying wrong. It cannot be attained in an open flask just because it is a condition that the reversible reaction can only be attained in a closed system. Now let's see what happened when this reaction happened in a closed flask. If we heat CaCO3 in a closed flask, you will see that carbon dioxide cannot escape out of the bottle, and after some time carbon dioxide and CaO are again reacting to form CaCO3, the reverse of the above, and hence both of the reactions are taking side by side, decomposition and combination. Both are happening at the same time, and an equilibrium rate is established, and the rate of forward reaction becomes equal to the rate of a reversible reaction. In these two reactions, decomposition is reverse of the combination or vice versa when calcium carbonate is heated in a closed flask so that carbon dioxide can't escape out as shown on the figure. Initially only decomposition takes place on forward reaction, but after a while carbon dioxide starts combining with CaO to form CaCO3, reverse reaction. In the beginning, forward reaction is fast and reverse reaction is negligible or slow. But eventually the reverse reaction speeds up and both the reaction goes at the same rate. At this stage, decomposition and combination takes place at the same rate but in opposite directions. As a result, the amount of calcium carbonates, calcium oxide and carbon dioxide do not change. It is written as CaCO3 reversibly goes to form CaO and CO2.